So that for giving proper introduction, I added this this part, introduction to composite material. So here, aluminum composite, particularly ex-situ composite, I think you will get the material. It is globally, you have material available, plenty of material available in literature. But in-situ composite, it is very limited. Very few people are doing research. So I want to explain the synthesis, the in-situ composite, and what are all the challenges I faced while doing my synthesis, and various machinability studies conducted through my students. So here, whatever work I am presenting, I done through my students research group and the funded research part. So as a teacher now, you have a outcome-based education is always trend. At the end of webinar, you can able to synthesize aluminum-based composite and microstructure mechanical properties, conducting machining studies within the lab. Then collaborate with students and conduct the project work on aluminum composites, mechanism of material removal for various machining process. I have seen some of the papers, conference level and some national level journals. Some people simply they are making their observation. Simply cutting speed increases, surface roughness decreases like that. Why it is decreasing? So with respect to process parameters and material basis. So both point of view we need to explain. So that is missing. Once if you are understanding this, so definitely we can do the paper at a higher level.
Sir, 1 minute, sir. Once again, share the screen, sir. Somebody has joined. Again.
Yeah.
Okay, sir. Thank you.
Right. So for I go to composite material. So composite material, it is a combination of two materials. Both are in heterogeneous nature, and finally both are combined together. So here that two materials, one is called matrix and another one is called reinforcement. So these two matrix and reinforcement are combined together to form the composite material. So here, if you look at the composite material, the matrix phase is extremely ductile. The reinforcement composite, normally they are selecting ceramic particles. So the soft, generally matrix material, for example, if you talk, aluminum is widely used as a matrix material. We know the nature of aluminum; it is highly ductile material. Reinforcement, you take an example of silicon carbide, SiC, right? So SiC is a ceramic particulate; it is extremely brittle.
Yes, sir.
In composite material.
Hello, sir.
Yeah.
What you are saying, the screen is not visible, sir.
Rupa, what happened? Somebody is sharing?
The presentation is not visible.
Just a minute, sir. You be in mute on. I will come.
Yeah, Ropa, at present Ropa is sharing her screen, sir, but if it is not available.
Just a minute, sir. Just a minute, sir. Sir, now it is visible? Sir, now it is visible?
Yeah, it is visible, sir.
Right.
Yes, sir. Okay, sir.
But I am not seeing. Can you see my screen?
Yes, sir.
Right, sir. I will start. So the composite material title is there, no, on screen.
Sir, it's clear.
Yes, sir.
Sir, you can start, sir. You can start this presentation, sir.
Okay. Are you viewing screen? Are you viewing my screen? Composite material slide is there?
Yes, sir, we can view it.
Sir, yes, sir, we can see, sir.
Okay, sir, fine. If any interruption is there, you tell me, sir, I will change, okay? Right. So composite material already I introduced. It's a combination of two material. One element is matrix and another element is reinforcement. So matrix is very soft and ductile. Reinforcement is very hard and brittle. Right, sir, participants, please mute it. So I am getting unwanted noise. Please mute. If you have any problem, you mute on and answer. You tell me, sir. Okay. Right. Matrix and reinforcement. Here, the matrix is soft and ductile. Reinforcement is hard and brittle. Here, if you are combining together, the hardness and strength of the material is greater than the matrix and less than the reinforcement. Whereas the ductility and toughness, when compared to reinforcement, the composite material have better, and when compared to matrix, the ductility and toughness is low. The industry and material scientists, they define the composite. They define in different way. It's a new material with the different properties are compared when compared to this. So here, once the composite is made, the composite property, it is in between the matrix and reinforcement. So I will go to next slide. So next I go to the history of the composite. So I request all the participants please mute. So my voice is totally not audible. Right. I go to history of the composite material. The composite material now it comes to late 80. It came, and in India late 90s. So many of the scientists from IITs, NITs, they started their research work. So this research is previously available in 400 BC. We have laminated writing of material from the papyrus plant. So this plant. Then 1300 BC, Egyptian and Mesopotamians used straw bricks. So this is the straw bricks available. So and 1200 AD, Mongolians, they invented first composite bow. So these are all the the composite material available at olden days. So next, further the history of composite. Hindu civilization, 300 BC, you have strawberry reinforced brick. Straw plus mud brick, it is available in 3000 BC. And samurai, it is also, they made a composite formed, it's called laminated. So laminate also comes under the composite. Steel composite, they formed by repeated folding of steel bar back on itself. So repeatedly folded, and finally they make a sword. So it is like this. So this is a laminate, is one kind of composite. Then later on, 1800 AD, Industrial Revolution came. And same composite technology, people, they started composite and cast iron. Then modern composite, 1950 onwards, we have fiber reinforced composite, it is available. Next, I go to the classification. The classification of composites, we have particle reinforcement, fiber reinforcement, and structural composite. So particle reinforcement composite, you have a larger particle and smaller particle. Yeah. Rupa, can you hear my voice? Rupa, are you online?
Yes, sir.
What slide
Yes,
is on
sir.
screen?
I am in online.
What slide is on
Composites,
screen?
sir. Classification.
Right,
Classifications of composites, sir.
Very good.
Okay.
Man.
Sir, again, 1 minute, sir. Sir, my sincere request to everyone, sir. Please don't share your screen and mute your mics and videos, sir. Again, Vijay Kumar Reddy is presenting the screen. Sir, Vijay Kumar, sir, can you please stop presenting? Sir, again, you need to present, sir.
Please, you control the screen and unmute it. Don't give anyone to screen share, please.
No, it is not possible for some reasons.
Sir.
You
Yes,
should
sir.
keep your screen off, okay?
Rupa, my slide is there?
No, yes, sir.
Okay, now can I proceed now?
No,
Classification.
sir.
Sir, you can proceed, sir.
No, sir. 1 minute, sir. No, sir. It once again present, sir. Actually, it's not visible.
Okay.
No,
Madam,
madam,
you
it
can fill the
is
screen, madam.
visible. The thing is, you never give shares screen share to others.
Sir, that option I could not control here, sir. That's why I'm requesting everyone to not to present the screen, sir.
It's my knowledge that control is with you only. Okay.
No, no, sir. Who will meet? That is not
Okay, sir.
possible. Please understand that who will meet? It is not possible.
That's why they never touch
Okay,
it
sir.
in install.
Rupa came.
Ha, sir. Now 2
Okay.
minutes, sir. It's loading.
Is it came?
Ha, sir. Yes, sir. Now it's
Right.
visible, sir.
Right. Okay.
Okay.
So I request other participant, please be in mute. So I'm getting unwanted noise. Okay. I go to composites. I mean classification. Composite is classified into 3 categories: particle reinforcement, fiber reinforced, structural reinforced. Particle, again, we have large particle, dispersion strength. That is a small particle. Nowadays, microparticles and nanoparticles like that. Nano composite, it comes under this category. Then fiber reinforcement, you have continuous and discontinuous fiber. So continuous, discontinuous fiber, long fiber, short fiber. So short fiber, it is called as a whisker fiber. Again, the discontinuous fiber, you can keep it aligned way and randomly oriented. So depending upon our property requirement, you can go for aligned and randomly oriented. Again, structural composite, it's called laminate. Laminate, I said the example. There is a sword made by repeated folding of steel material and made. So this is called laminate. So sandwich panels, so these are all the composite comes under structural. Again, the classification. Yeah, composite with respect to matrix and reinforcement based. So matrix based polymer matrix, metal matrix and ceramic matrix. Reinforcement based, you have fiber reinforced, whisker reinforced and particle reinforced. So next I go to, I want to discuss an important composite material. So this is the graph plotted specific strength versus the specific stiffness. So these two properties are more important for real-time application. So here you have specific strength for rubber, foam, this kind of material. It is low. Both specific strength and specific stiffness, both are low. You look at our composite, it is at middle. So moderate specific strength and moderate specific stiffness. Whereas you have a ceramic phase, it is available. We have an extreme specific strength. That means good strength to weight ratio and extreme specific stiffness, good stiffness to weight ratio. But the ceramic particle.
Sir, sir, once again, sir, small
Yeah.
request. Small
Yeah.
request.
Yeah.
Sir, Vijay Kumar and some other are sharing the screen, sir. Actually, I don't know
Sir,
why this.
I don't know Vijay Kumar Reddy, why he
If it is not visible.
repeatedly doing this. Vijay Kumar Reddy,
కృష్ణ గారు ఉన్నామండి ఒక్క నిమిషం
Sir, otherwise I will share the screen, sir.
no, that it is difficult. Let us say. I think Vijay Kumar Reddy and others, they will keep quiet hereafter.
Okay, now they're
Sir, you
not
can continue,
presenting.
sir. Sir, now
Right.
you can continue, sir.
Right.
Yes, sir,
Specific strength.
continue, sir. Continue.
That graph is available. That
Yeah.
graph is.
Again,
Sir, we can see your PPT, sir. You can continue, sir.
Yes, sir. Yes. Specific strength and good stiffness ratio. Here, you look at the ceramic. We have extreme specific strength and extreme specific stiffness. So both are high, right? But the ceramic we can't use. It is a very limited use. If you want to utilize the material, the hardness and stiffness alone, it doesn't support. So ductility is a very important thing that is required. Without that, we can't change it into the required component, right? Next, I go to the properties. So here, these properties are comparatively available when compared to, already I said, composite material. The property always in between the matrix material and reinforcement. Comparatively, when compared to matrix material, composite material have higher tensile strength, then higher hardness, right? Higher specific strength, right? So all the required strengths are there, and right, composite part eliminate joint and fastener, then improved appearances. The composite material we can get right? Good corrosion resistance. So these are all the properties available. So I request participant, please be in mute. So you are disturbing. You are chatting with your family. It is audio. I'm hearing. Please mute.
PPT is not visible.
Sir,
Rupa.
PPT is not visible, sir.
Right.
Sir, PPT is not visible, sir.
Just a minute.
Yes, sir.
Now it is there.
Sir, it is visible, sir.
Okay, fine.
No, sir. No, sir. It's not visible.
Ma'am, you should ping the sir this one,
Pin
ma'am.
the screen, madam.
Ping the screen, ma'am. You
I have
can see,
pinged,
ma'am.
sir.
Is visible
Sir,
now?
I have.
Yes, sir. Sir, it is visible,
Yes,
sir.
sir.
Right, I will proceed. Okay.
Madam, just pin the screen, madam. You can only
Right.
visible the screen.
Right. So next I go to properties of carbon composite. So reason for addressing this property, carbon fiber, carbon matrix composite, it is widely used in aerospace and space application. This is excellent thermal shock resistance. Then low coefficient of thermal expansion, high modulus of elasticity, high thermal conductivity, low density, high strength, low coefficient of friction, thermal resistance in non-oxidizing atmosphere, high abrasion resistance, high electrical conductivity, non-brittle in nature. So this is the these are all the because of these above said advantages of carbon fiber composites. It is widely taking application in aerospace and space industry. Then again, further application, you can use the composite at bulletproof aircraft, automobile parts, boat hulls, sports kits, helmets, and building construction. These are all the area. And again, the composite material used in some automobile, helmet, golf bat. So this is a micro unmanned aerial vehicle. Then again, shipbuilding, then automobile, tank fabrication, aerospace, space. These are all the applications it is using. Then you take the composite material in Boeing 787. You look at the usage of composite material. They are using 50% of the material. It is made by composite material. Then again, composite material in automobile field. Here in BMW i3, they are using composite material. So I thank the people. So it is already available in net. This source of this information. And according to the source, here you look at the weight reduction. Previously, the weight of the car is 1275 kg. Then after application of composite, it was reduced to 420 kg. So this information I got from this website. Then again, some of the application in Indian defense. So according to R.K. Gupta, so it is composite section made by composite material. Then flux nozzle, re-entry vehicle structure (RVS). Then composite rocket motor. These are all the materials. These are all the material. It is used in defense applications. Then again, composite.
Excuse me, sir.
Yeah. Yes. Tell me.
Sir, PPT is not visible, sir. PPT is not visible, sir.
Right. You pin it. Now visible, no? Now visible, no?
No, sir.
So go through participants. You just see the right
Madam,
side
please
column.
pin the screen,
Pin is
madam.
there. Just click it. You pin it.
Click it.
Yeah,
Click
pin
it.
Pin the screen, you can
Right.
pin the screen, madam, without any
Right.
problem.
Okay, sir.
Yes, sir.
Okay,
Now
sir.
I have pinned, sir.
Right,
Sir, I
very
have
good.
pinned it, sir. Now
every
is it
time you-
visible, sir, for everyone?
Okay, fine.
Okay, sir.
Other participant, please be in mute. Right, here, composite penetration in major sector. Wind energy, it is having highest penetration, wind energy applications. Then mass transportation low, so descriptions are already available. What kind of composite it is available? Building and construction medium, oil and gas low, agricultural low, military defense low, and E&D and the chemical corrosion. So the application is medium. So I request all participants, please mute. Then only I can start. Please be in mute. Please be in mute. Rupa, mute cheyma. Rupa, are you?
Sir, 1 minute. Yes, sir. It's audible, sir. I will see, sir. I will mute, sir.
You mute
Again,
everyone.
some. Oh, okay, sir. Okay, sir.
Right. So
Now
composite
it's muted, sir.
right, okay. Composite penetration in major sectors. So here chemical, corrosion and 3D printing. So these are all composite material penetration into the major sector. Then application of fiber reinforced composites. We have aircraft and military application. Space, in space they are using boron fiber reinforced aluminum tubes, Kevlar epoxy pressure vessel. Then automotive bodies, they are using chassis, engines. Then sports foot for weight reductions, they are using composite. Marine application, boat hulls, decks and bulkheads. Malla mute on chestunnaru, mute cheyandi.
Yes, sir. Sir, 1 minute, sir. I'm doing, sir.
You please mute, I will proceed further.
Okay, sir.
Right. So next I go to the matrix and reinforcement. What are all the in composite material, in lakhs and lakhs of composite materials available in literature. So among that, what is the source already I presented? The usage of matrix material, usage of reinforcement. So the usage of matrix material, aluminum, it is widely used. Then apart from that, you have ferrous, then titanium, nickel aluminide, then Ag, so magnesium. These are all available. In aluminum matrix, in aluminum matrix composite, it is widely used. Then you look at the magnesium. So magnesium also, when compared to aluminum, it is a lighter material. There is a more potential to get the weight reduction. But problem is aluminum material, magnesium material, you cannot melt like aluminum. So once if you want to melt, then it will explode. You need to make some special arrangements for magnesium-based casting, so that the commercialization of magnesium material, it is very difficult. So that the explosion, because of its property, you can't melt. If you want to melt, magnesium will explode. So if you are finding any new technology to process the magnesium-based composite, if it comes to real-time application or commercial application, definitely we will get a good reduction in weight reduction, right? So next I go to the various particles used. SiC, Al2O3, boron nitride, tungsten carbide. These are all the particle it is used. So recently, this is a data updated with 2012. Recently, people they are using PiB2, ZrB2, B4C. So these are all the super abrasives also used. So SiC, Al2O3, it's a conventional abrasive. Cost is very less. Other abrasive like ZrB2, PiB2, this kind of Rupa, again somebody, Ravisegar, somebody opened, Ravisegar or somebody, they opened the screen. Rupa?
Yes, sir. I have muted, sir, and I pinned the screen also, sir. I don't know why, but your screen only visible, sir.
Okay, fine.
Okay, sir.
Right.
Yours is visible, sir.
Right, fine, ma. Short fiber, we have carbon, SiC, Al2O3, SiC2 plus Al2. These are all the short fibers they can use. Then continuous fiber also it is available, Al2O3. Then nanoparticle, carbon, Al2O3, SiC, these are all available. Carbon nanotubes also available. It is, you look at this, less than 100 nanometer. So next I go to, so I want to address the property when by comparing metals. So this information I got, this is a traditional one, but still we can get some important properties. So material is homogeneous in metal. That means here I am talking about metal. Here I am talking about composite.
Sir,
material,
PPT is not visible, sir.
Okay, just a minute. I will again go to screen share.
Sir, I will pin, but PPT is not visible.
Yes. Somebody opened. That is a problem. All right. Now you can see.
No, sir. Presently, it is not visible, sir.
Yeah, I'm doing. Wait. I think now it is okay. Yeah.
Yes, sir.
Right.
Yes,
Please,
sir.
Yes, sir. Yes, sir.
Yes.
Yes, sir. Sure.
Oh, fine, sir. So material is homogeneous. Here material contains particles, particle matrix, and particle interface. 3 components are there, but it is not homogeneous. Mechanical properties are constant, but here mechanical properties are often changed. Whenever you are, for example, you take a micro hardness, if indentation is fall on matrix material, it will show less hardness. If the indentation is falls on matrix reinforced interface, it is moderate. If indentation is false on reinforcement, it will show more. Then compressive and tensile strength approximately equal in magnitude. Compressive strength is greater than the tensile strength. Here, fracture toughness and ductility are high. Here, the fracture toughness and ductility are relatively low. So, material is ductile under both tension and compression. So, here material is ductile under compression, but brittle in tension, right? Because of that, we are getting more tensile property. Then again, Rupa, you meet somebody, they are giving disturbance. Please mute that. Please mute all of them.
I have muted, sir. I'm checking and I'm muting, sir.
Right. Failure is due to localization. So here a failure is due to either fracture or decohesion of particle. Then residual stress due to cooling down from fabrication or annealing temperature are minimal. Here residual stresses are induced. Residual stresses are induced in the composite due to mismatch of thermal expansion, coefficient of thermal coefficients between matrix and particle. So again, come to compressive strength increases under impact condition. Here, compressive strength is increased under dynamic loading. So this is one of the advantages for using composite material. And again, metal exhibits work hardening. Here, MMC exhibit work hardening also. Both will. Here, thermal softening is upward. Here, thermal softening is gradual. Right. Next slide. Yeah, specific application of composite. So if you go to any interview or anywhere, if you are talking about composite material, the interview people, the interview personnel, immediately they ask, what is the exact application of aluminum composite? You tell me like that. So there I got this information from this particular paper. So aluminum SiC composite, it is used in piston, brake rotor, propeller shaft, connecting rod. So what is the advantage of this? Because of this advantages, it is taking application. So directly you can answer if it is asked any question. Okay, SiC composite, it is used in piston, brake rotor. Like that, you can answer. Instead of asking automobile industry, automobile applications, instead of that, you can go for specific. Then again, aluminum silicon composite, aluminum SiC particle, SiC whisker also, it is used. Then aluminum oxide short fiber, it is used in sprockets, pulley and covers, piston ring, piston crown. These are all the area it is used. Then aluminum oxide, this is Al2O3 reinforcement, long fiber, it is used in connecting rod. Then copper graphite composite also used in electrical contact strip, electronic packaging and bearing. Wherever the electrical conductivity is essential, that copper composite. So here one can understand aluminum composite and copper composite. So people widely they prefer the aluminum based composite because of two reasons. One reason is when compared to aluminum, copper, it is relatively costly. And if you are selecting copper matrix, it will not give weight reduction. That is the problem, right? Copper material, it will when compared to aluminum, the density of copper is more. So, so that the weight reduction potential is very less. But however, copper material having, when compared to aluminum, greater strength, good ductility, everything is there. But because of the higher density, which replaced the aluminum. Then aluminum graphite, it is used in cylinder liner. The aluminum graphite reinforcement. Once graphite is reinforced into aluminum matrix composite, the wear property will improve. Whenever sliding, the graphite, it will act as a lubricant and it reduces the wear rate. Then aluminum titanium carbide, aluminum TAC composite, again used in piston connecting rod. Then aluminum oxide fiber, carbon fiber, it is used in engine block. Then superalloy based composite, already I said in matrix, nickel also you can use it as a matrix material. Ni3NB, this is used, this composite, superalloy based composite, it is used in turbine blades. Then again copper niobium, so copper tungsten, these are all the composite material used in superconductor and spot welding electrode. So these are all the application. Hereafter, if anybody asked what is the specific application of composite, directly you can tell. Then commercialization of composite. So composite material, you know, it is having many advantages, right? Many favorable properties are there. But what is the challenges in commercialization? So this commercialization of aluminum matrix composite, Here GORC ETAL 2019 very clearly described the commercial scale production of aluminum-based composite aimed at industrial application has grown. Previously, the industry people, they denied to apply the composite, but last few years, particularly they started to use. So since many companies from China have entered into the market, right? Previously, the people denied to use. Right, the China market, they came forward and they are making a lot of aluminum-based composite. Then compared with the large-scale production of aluminum-based composite, use of metallic composite is very low. So almost all the manufacturers have started using aluminum-based composite material in production for very small unit at the gained merchandise. So finally, here I want to inform is the aluminum-based composite. With respect to aluminum-based composite, China is one of the biggest aluminum-based composite manufacturing country in the world. So it is his statistics he conveyed.
What?
Then the challenges. So what are all the challenges? Challenges to use. The number of issues to be addressed to advance the commercial application of aluminum-based composite, similar to other. So here a cost to performance ratio, aluminum-based composite is greatest concern for the industries. So this is for making low volume production. If you are increasing volume, definitely it will comes into control. The cost of aluminum-based composite is not a big challenge to compete with other existing material. However, when aluminum-based composite will get optimum application in industries, when manufacturers start to make a profit from material is still the question. So overall, it is expected that very soon the large-scale commercial utilization of aluminum-based composite is going to happen. So that all the researchers who are interested to do composite material, particularly aluminum-based composite, so definitely you can do. Next slide. I come to aluminum-based composite. The aluminum-based composite you can synthesis in two ways, right? Two categories, namely ex situ synthesis and in situ synthesis. So ex situ synthesis is a process in which reinforcements are directly added into the molten matrix. So here I want to explain what is how the ex situ composites are made. Ex situ composites, it is available in many methods. Powder metallurgy based composite, it is widely available in literature. Powder metallurgy, aluminum based composites are made by powder metallurgy. Rupa, mute cheyma walla.
Sir,
Right,
mute
thank you.
chestnut, sir.
Right, ma, right. So powder metallurgy, the various processing, powder metallurgy, reactive hard pressing, spray deposition, rio casting, squish casting, stir casting. So various methods are available. So I am putting the reference here. So if readers, if you want to have further information, you can visit his paper, Ramanathan Arunachalam, 2019. So here in the literature review, we can clearly say that two process of ex situ synthesis, it's widely used. One is the powder metallurgy, another one is stir casting. So stir casting setup, it will be available. There is a motor, so that motor shaft consists of stirrer. There we are adding aluminum material and the reinforcement particle. For example, matrix material, aluminum, right, scraps or pieces we are putting. Then reinforcement they are putting, right, molten aluminum melt, reinforcement particles are added, then stirrer. So purpose of stirring to get a uniform distribution, right? Here you have a resistance coil. So after that, you have a bottom pouring attachment. Stirring, everything is over. Finally, this aluminum particle, aluminum matrix composite. So here you will get, after stirring, you will get aluminum matrix composite. So finally, through the bottom pouring attachment, you can pour it into the mold cavity. If you want to make a rod, if you want to make a plates for testing various property, it is possible. So next to stir casting, another important process widely used is powder metallurgy process. So here aluminum powder is there, SEC powder is there. I think all the mechanical engineer, you know what is meant by powder metallurgy. Metallurgy and material science, this topic always available. Aluminum powder and SEC powder, both are mixed with a particular proportion. Then finally, by using cold press, the compact are prepared. By using cold press, the aluminum, the composite compact is prepared. Then again, what happened? It is hot pressed, the cold press. Then again, here they are doing hot press. Then after that, the hot pressed composite, it is again extruded. So after extrusion, we get the metal matrix composite. You will get the metal matrix composite. So here mixing, after mixing, cold press and hot press. Cold press, while doing cold press, the porosity is a little bit reduced. Then again here they are doing hot extrusion. So hot extrusion, while heating, the homogeneous of composite material is improved. Then further extrusion, if you are doing extrusion, so then what happened? The property, it will be improved, particularly mechanical property. Hardness, strength, this kind of property, it will be improved while doing extrusion. So these are all the various steps. So next, right. So now I want to talk about challenges and limitation of extruded composite. So this I am telling because you people are interested to make a composite in laboratory. I mean laboratory, or if you want to do your project, or if you want to do your research. So please look at this. This composite material extruded process suffer with the presence of reinforcement cluster, poor wettability between the matrix and reinforcement, and thermodynamically unstable. So these are all the challenges. The composites are made by using this extrude process, whatever extrude process I listed. So this is the main problem. Okay, reinforcement cluster formation, poor wettability. Reinforcement cluster means wherever reinforcement cluster is there, while going for application, that the cluster portion immediately you will get a crack. Crack propagation is initiated. So once the crack propagation is initiated, then immediately the material start to fail very quickly. The crack initiation, it will be started at the reinforcement cluster. So that it is important to distribute the reinforcement particle into the matrix uniform way. Okay. Then size of the reinforcement particle of the composite which is synthesized. So extruded is fairly more. So here normally the extruded composite people, they will go for 60 micron, 80 micron. So this kind of bigger particle, 60 micron, 80 micron, this kind of bigger particle. People widely they go because SAC and Al2O3 60 micron, 80 micron, the cost is very low. Per kg, 650 or 700 you can buy it, right? 60 micron or 80 micron. So cost is very cheap. So people try to use that bigger particle. It will create a lot of problem. So therefore, bigger size particle yield poor dispersion into the matrix alloy. If particle is small, the dispersion is very easy, right? If particle is bigger, 60 micron, 80 micron, the dispersion is very poor. Then again, presence of clustering and agglomeration of reinforcement particle result heterogeneous microstructure. You will get a heterogeneous microstructure. So once heterogeneous microstructure, then what happened? That wherever reinforcement cluster is more, again, that place the crack is initiated. Generally, reinforcement contain dust as well as oxide layer. So the reinforcement you are purchasing, I said no, you are purchasing reinforcement, SAC, right, Al2O3 something, that SAC and this particle, always it will conduct, it will with a lot of dust and oxide layer. These are all the problem. Again, the dust and oxide layers are there while putting into aluminum melt. The dust particle and oxide layer, this will react with aluminum. There it will make some intermediate component that will dilute the mechanical property. That particle dispersion strength, it will be decreased. Then existence of these impurities minimize the wetting, right? Matrix reinforcement directly it need to stick together. Matrix and reinforcement both should stick together. If in between, because of reinforcement, if contains any impurities, that impurities again what happened? It will affect the interfacial bonding strength. Okay, existence of impurities minimize the wetting between the particle and leads to poor interfacial bonding strength. If bonding strength is low, automatically what happened? Tensile strength. If it is go for application, it will fail very quickly. So we are expecting tensile strength in very high. Because of this problem, then it will fail very quickly. Then, so another important limitation, challenges and limitation in AL-SiC composite system, SI is thermodynamically unstable. Because why I am sharing this is AL-SiC composite, aluminum SiC composite material, it is widely used. What is the problem? SiC is thermodynamically unstable. That is a problem because SiC particle, it is very cheap among all the reinforcement. So people they will prefer. And if you are look at literature, composite material have a very high strength, everything. And people he is making right? He is making into the foundry or in his laboratory. Finally, if you are testing property, you will get a very lower property. I think I have this experience also, right? In our laboratory, one time we tried to make this SiC composite, aluminum SiC composite. In literature, I selected AA 6061 because it's a low cost alloy. AA 6061, it is a very low cost aluminum alloy. SiC is a very low cost reinforcement. We purchased this, and we have one furnace in our electric furnace in our college. We make a composite and we gone for testing, right? We gone for testing. So then what happened in literature, they are telling very huge value. They are telling 200 MPa, something like that. We are unable to get even 50% of the strength, what they are saying in literature. So immediately, I searched the literature. So here, what happened, while melting aluminum alloy, right, melting aluminum alloy, 550 onwards, the melting will be started. So around 600 degree completely, it will be at liquid state. If you are melting your aluminum alloy or your aluminum melt is reached 660 or around 700 degree, if you are putting SiC particle into this, then what happened, we will have this Al 3 SiC. So instead of SiC composite, it will form an intermediate component, Al4C3, right? Al4C3 and Si. So this intermediate reaction will happen. So after 660, okay. If you are melting up to 600 or 620, up to 620, there is no problem. Reaches beyond 660, you will get this Al4C3 formation. This Al4C3 formation, once it comes, immediately the mechanical property will be get. Because of many people will confuse. They will do it in their laboratory. Because what happened, these people, they did not control this temperature. Simply keep on melting, applying heat, everything. Okay. This is the problem. Because of this intermediate component formation that reduced your mechanical property. You need not confuse. So this is the actual, it is happening. Okay. So one time I faced the problem. Then again, what happened after studying this literature, interfacial reaction, this particular paper, this particular source, it is clearly explained. The brittle Al4C3 is largely insoluble in liquid aluminum forms, either continuous layer or discrete precipitates around the SiC particle. This SiC particle, then what happened? If this composite material goes for tensile test, immediately it will fail. It will show 40%. Literature, they will give some value. You will get 50 to 60%. So now I am clearly telling, if anybody go for Al SiC composite, you don't give your temperature more than 660, right? Then only you will get a good strength. So next, I am going to aluminum in situ composite. So far I discussed the ex situ composite. Now I am going to talk about the in situ composite. So here in situ composite, ex situ composite, I got the Shudganga infield. This website, I got both picture. So this picture in situ composite, it is already available for a very long time. Or someone, they developed this and put it into the thesis. So I got from this. So this picture very clearly explained the difference between in situ composite and ex situ composite. So first I'm going to talk about in situ composite. What is in situ composite? Then I will compare. First of all, in situ composite is a process. The reinforcement is synthesized by chemical reaction within the melt. This process can overcome many limitations comes from ex situ synthesis. Right? Here you look at here in situ composite, the reinforcements are synthesized chemically. Right? Here we are taking halide salt. Here your matrix material is there. Then finally, if your halide salt reacting with aluminum melt. So here what to do is, you melt the aluminum material up to 850 degrees centigrade. Why 850 degree? I'll inform later. Then halide salts, K2TAF6, K2ZRF6, KBF4. These are all the halide salts you can mix, right? After reaches 850 degree of matrix, then you added the preheated halide salt. Put it into that. Then if you are making stirrer, here what happened, you will get the in situ composites. Right? Here, in situ, we are not purchasing. For example, in situ method, if you want to synthesize TiB2 composite, you need not purchase TiB2. Through the chemical reaction, you will get it. So that what happened, the TiB2 everything is freshly generated, freshly chemically generated TiB particle. It will be introduced, it will be added with matrix so that you will get the lot of enhancement in the property. So now you look at this picture, another one, reinforcement. So reinforcement particle like SiC, Al2O3, Al2O3, B4C, this particle, what happened? Here you have a hot molten material, molten matrix is there, molten aluminum or something is there. Directly we are adding the reinforcement particle into that, then they are making. So here reinforcement, it is directly added. Here what happened? Through the halide salt, the reinforcements are chemically generated. That is the difference here. Okay. So here reinforcement, already I said, previous slide we discussed. So reinforcement particle always consists with impurities, dust, oxides, something like that. These impurities, oxides, everything, once going into the matrix, then the impurities, it will be available in between the matrix, and reinforcement. That interface, it will create some property deviations. Okay. So I go to next slide. So advantage of in situ composite, it's a fresh formation of reinforcement, make it pure and free from the contamination like oxide. Because in in situ synthesis, the TiB2, everything, it is freshly formed. Okay. So there is no scope for any impurities or any oxide formation, nothing. Then clean reinforcement phase is available, more cohesiveness between the matrix and reinforcement. So here, already I said, while adding the halide salts and matrix, there is a exothermic chemical reaction will be conducted. So that exothermic chemical reaction, which release the reinforcement. Okay. Then again, exothermic reaction means, which emits the lot of temperature. Then immediately your aluminum melt, it will be boiling. So that boiled aluminum melt, which distribute the reinforcement particle into uniform. So previously we are using stirrer, everything to distribute. Even putting stirring, everything also, it is very difficult to control the distribution. Here what happened, due to exothermic chemical reaction, the aluminum melt is, what happened, boiling. It will be boiling. That boiling, what happened, uniformly distributed. That boiling action, which gives some stirring. So that stirring action uniformly distributed. Result uniformly distributed. And finally, we will get the homogeneous microstructure. Once microstructure is homogeneous, definitely we will get good mechanical property. Then final point, composites produced by in situ have good thermodynamic stability, which gives better thermodynamic stability. Means here in SiC component, we discussed, this is called thermodynamic instability. Whereas here, this material, there is no thermodynamic instability. Okay. So reinforcement does not react with any the matrix material. Therefore, that also it is advantageous. So next here, in situ and ex situ, there is a literature, Kurvilla, right? He compared, he is taking 20% TiB2 in situ and 20% TiB2 ex situ, right? 20% TiB2 he is taking constant, right? And here he is using ex situ composite. That means 20% TiB2 chemically generated and 20% TiB2 they are physically added. Okay. So physically added, it is called ex situ. Chemically generated, it is called in situ. Okay. So here the analysis of mechanical property shows that the in situ composite, in situ 20 TiB2 has more than 49% of improvement in UTS, ultimate tensile strength, and 22% improvement in hardness than the ex situ 20%. Okay. So this particular paper, Kurvilla, is very clearly described. So definitely we will get a very good improvement because of that chemical reaction, the boiling action, distribution of uniform distribution of particles, and the thermodynamic stability of this sensitive process, which makes the 49% means around 50% enhancement. Okay, so that in that way, in situ composite is more advantageous. Now I go to synthesis of AA6061 in situ composite. So this is my personal work. So this is my personal work. So I need not cite anyone. So I'm just going to explain how AA6061 TiB2 in situ composite I developed. So pre-measured quantity of aluminum alloy, I kept it into the graphite crucible. So you purchase aluminum crucible and keep AA6061 alloy. Then the halide salt KBF4 and KTTAF6. Because if you are adding this KBF4 and KTTAF6 through chemical reaction, thermodynamic reaction, you will get the exothermic reaction, you will get the TiB2 synthesis. That chemical reaction I will show later. So here KBF4, K2TAF6 halide salt, this powder, it is called halide salt. The suitable quantities are preheated. So here KBF4 directly you can't add it into the melter. So you preheat up to 300 degrees centigrade for a few minutes. Right, the temperature of the aluminum alloy brought up to 850 degrees centigrade. So why 850 degrees centigrade? I will explain later. Because that 850 degrees centigrade only, we will get the reaction. Okay. So less than that, it is not difficult. It's not possible. 850 degree aluminum melt. First what to do? Put your aluminum scraps into your crucible and melt up to 850 degrees centigrade. 550 to 600 range, the aluminum metal, it goes into liquid state. Okay. After reaching the liquid state, you maintain 850 degrees centigrade. You keep proper thermocouple and maintain 850 degrees centigrade. At 850 degrees centigrade only, the KBF4 and K2TiF6 will react. Okay. Then the preheated salt and mixed into the molten. Preheated KBF4 salt mixed into the molten metal. A graphite rod also used to stir the melt. Graphite rod is used. This stirring of molten alloy, was continued up to 20 minutes. So 20 minutes continuously you need to stir. While stirring, the reaction will take place. KBF4 and aluminum melt reaction. So aluminum alloy reacts with salt and by exothermic reaction, and the temperature of the melt was reached 1250. What is the input temperature you given here? Aluminum matrix is 850 degrees centigrade. After adding this KBF4 and K2TiF6 powder, halide powder, due to exothermic reaction, suddenly your melt, it goes to 1250 degrees centigrade. So input is 850. After adding the salt, the temperature will increase 1250 degree centigrade temperature. So this temperature, higher degree temperature, it's a result of exothermic reaction. It is happening in 2 steps, right? First step is, at first K2TiF6 and KBF4 react with molten aluminum alloy independently and formed intermediate compound Al3Ta and Alb2. So Al3Ta and Alb2, it's an intermediate component. First, 1 minute, I will move this. I will keep it here, yes. So this Al3Ta and Alb2 reacts together, and finally it forms TiB2 and cryolite slag formed. So this also, so many people, many researchers, they will do that. They need to maintain 20 minutes time. So after adding this stirrer, within 10 minutes, some people, they will remove it. They try to pour it. If you are not maintaining 20 minutes, then you will not get TiB2. You will get only Al3Ta and Alb2. The Al3Ta and Alb2, again, you can't get the required property. So Al3Ta, Alb2, both are very higher in, these are all intermetallics. It does not have good thermodynamic stability, right? So these are all the problems are there. After 20 minutes, you will get TiB2 and cryolite slags are formed. The cryolite slags photograph I have, I will show later. So next I go to the equation. This is the chemical reaction. I said already, I will show later. So TiF6, 3 aluminum. So this is a 3 Al, 13 Al, it comes to aluminum melt. So Al3Ta, KAlF4, K3AlF6. So these are all the component will come. So the KAlF4, K3AlF6, these are all called slag formation. These are all called slag formation. This is called as a cryolite slag. Okay. So now you look at this, the KBF4 react with aluminum. KBF4 react with aluminum. Again it forms. So K2TiF6 independent. KBF4 independently react with aluminum. So the K2TiF6 gives Al3Ta. KBF4 gives Alb2. So again KAlF4, it's a cryolite slag. Okay. So again, if you are allowing more than 10 minutes, again this Al3Ta and Alb2 both will react. So I am putting here third equation. Al3Ta, Alb2 come from here. So both are reacting together. Finally, you will get TiB2. Al3Ta and TiB2 will form. So finally 4Al. So this KAlF4, right, and K3Al, so K3AlF6, these are all emitted from this reaction. So everything, what happened, it will be formed as a slag. It will come to this layer. While stirring, it will be floated on the molten metal. While it is floating, I think, it is very easy to remove. Take some spoon, iron spoon or something, you can take, right? This KAlF4, something like that. Okay. So once if you are removing all the slag, finally you will get Al and TiB2. Okay, Al and TiB2. So this TiB2, this is called in-situ synthesis. TiB2 is a ceramic material. Aluminum is a ductile material. So through chemical synthesis, we got pure Al, Ti4. So one important thing I am clearly given here. So you need to clearly remove the slag. That is important. Without removing the slag, again, if you are pouring, then the slag trapment, it will give a problem. The slag photograph, it is available in next slide. Right here, after removing the slag. So cryolite-like phases, it will be available like this. Right? No problem. It will be available at the top of the crucible. Right? Aluminum melt is there. Top of these slags are floating. So that what happen, easily you can filter out. You can take some spoon, you can remove it, and directly it is pouring. You can pour it like this. After removing the slag, you can pour it. Once if you are pouring, you will get AL TiB2 institute composites. Okay, so this is a processing step. So now I want to discuss the microstructure, how the microstructure it will be. Okay, so already I said we claimed a lot of advantages of institute composites, like homogeneous distribution, that the homogeneous distribution result good mechanical property. Apart from that, if you are going to the microstructure analysis, you can see one important thing. So this microstructure, even I have many microstructure. This particular microstructure, it is very clearly available. The TiB2 phases, always it will be like a hexagon phase. Okay. So this particular author, Sambat ETIL, is from IIT Madras. He very clearly shown, in his view, very clearly shown. It is a 2000 magnification and 20 micron. 2000 magnification, he got it. You look at that, all the TiB2 particles, it's all are hexagonal shape in nature, right? Hexagon. So this hexagon shape, it is very easy to bond with aluminum metal, and it will give. Again, you look at this. This is a ADAX graph. ADAX graph. The Ti phases are available here. Ti phases are directed here. Then aluminum alloy is there. That is a major element. Again, the SI it comes from here. We are using AA6061, right? This graph is mine. Okay, AA6061 alloy. So AA6061 silicon alloy. Silicon is the one of the alloying element. So that also detected. Okay. So here aluminum is there. Titan Ti is there, so that titanium boride particles are detected here. Okay. So next I want to explain an interesting thing. You look at this in SEM analysis. 50 again the same Sambat group they did at the 15,000 magnification, 1 micron width. You look at the TiB2 phase. It is hexagonal in shape. You look at what is the size of the TiB2 particle. He measured. Okay. So 1.56 micron, 1.45 micron. So you look at this 810 nanometer. The one side of the hexagon, the TiB2 particle is 801. So this is you don't think that minimum 1.6. So here he selected maximum particle size and given. Okay. So normally here maximum 1.5, minimum you can get it up to 800, 700, 800 nanometer at nano size TiB2 also formed. Okay. So here I want to share one interesting thing. If you want to purchase 1.5 micron of any powder, even TiB2 also, if you want to purchase per gram, the cost is per gram 1,000 rupees plus GST. Okay, 1 gram 1,000 rupees they are selling. Even you take JD powders, many commercial suppliers are there. 1.5 micron TiB2 or before say any composite material 1.5 micron. The cost comes out around per gram 1,000 rupees plus GST. Okay. Whereas if you are using this K2TiF6 KBF4 salt, you can purchase it for just 2,000 rupees. You can purchase, right? 1 K2TiF6, 1 KBF4, just 2,000 rupees. 1 kg K2TiF6, the cost around 1,500. This is around 700 to 800. So within 2,000, 2,500 rupees, you can develop this. Right, 2,500 rupees. What happen if you are purchasing halide salt and you can use it? Similarly, if you want to purchase 1.5 micron of TiB2 powder, external TiB2 powder, the cost is per gram 1,000 rupees will come. For example, if you want to purchase 20 grams of TiB2, cost of 20 gram is 20,000 plus GST. Okay, so this in this way, the in situ synthesis is very easy. Easily you can synthesize nano to micro composite. So next, now I am coming to the machinability study. In machinability study, I am going to discuss turning study, drilling study, grinding study, threading, laser drilling, EDM, and magnetic abrasive machining. So here all the work I am describing in this webinar, it is completely my own experience. Okay, so I need not cite anyone. So here, these are all my work I am doing along with my BTech student, MTech student, or my PhD students. So I want to first talk about the turning in situ composite, machinability study of in situ composite turning process. So turning process, so this work already I started at 2011. 2011 I published, 2010 I started. So investigation of flank wear, cutting force, surface roughness, right, in machining of 6061 TiB2. So this is the in situ composite. First I generated, I developed in 2010. So then later on, so we gone for a machinability study. So one of my friend who is working at NIT Trichy, and both did this, and we are doing along with the students. This is the photographic view of experimental setup. This experimental setup we did at Carmia University, right? CRDM. There is a machining studies lab is there, right? There I did. So experimental conditions. So we are selecting. We are using uncoated tungsten carbide because so here particle size are fine particle size and very smaller in size, homogeneously distributed. So that what happened, the impact on the reinforcement to the cutting material, I mean cutting edge, it will be very minimal. So that we gone for uncoated tungsten carbide too. And the cutting tool specification, we used the SNMG. This is available with the Carmia University. Then tool holder specification also, it is available with them. The tool material, we made it clearance angle is 7 degree, cutting edge angle is 75 degree, nose radius 0.8. So these are all the cutting tool nomenclature. Then cutting speed, we selected 50, 75, 100, 120, 150 meter per minute. The 150 meter per minute, I think really we struggled. Okay, we got little vibration on the machine. Then feed rate 0.1, 0.2, 0.3, 0.4, 0.5. So here up to 0.4 it is worked well. So again the 0.5 also we tried. Then cutting depth, we started depth of cut. Cutting depth means depth of cut 0.5, 0.75, 1, 1.5. 1.25, 1.5. Then reinforcement ratio, we selected 0, 3, 6, 9. So here, one thing you need to understand, this TiB2 composite by halide salt reaction, you can't make more than 90% of the composite material. I mean, 90% of the reinforcement. If you try for more than this, then of course the literature very clearly indicates that more than 9 we cannot go. But even though we tried, 12% we tried. So what happened? 12,000 tried because of exothermic temperature. So even 7.5% also we got around 1,500. Then what happened? While making composite at 12%, we are using cast iron die. It is upper half and lower half. Then we have connected together. Okay. So that upper half, lower half, that joining, we added the mild steel pin. That high temperature melted the pin, right? The die connecting pin, melted the die connecting pin, and the molten metal comes out. So that we are unable to do. This is my observation, cutting speed and flank wear. So cutting speed and flank wear for different reinforcement. So here, of course, 0% TiB2 means just AA unreinforcement alloy. The flank wear, while machining flank wear, the tool wear rate is very less for all the speed ranges. Then again, 9% TiB2, we have more flank wear. So 9% means the TiB2 content is more. So that what happened? More content, it will give the composite material itself, it will be abrasive in nature. Then so that excessive abrasiveness, excessive reinforcement content, they increase the flank wear. And one more thing, if you are interesting notice, when increasing cutting speed, the flank wear, it is keep on increasing. You look at that all, irrespective of reinforcement ratio, when increasing cutting speed, flank wear is increasing. So because here at a higher cutting speed, what happened? The friction will be more. At a higher cutting speed, the friction will be more. So that what happened? More friction, right? So that what happened? The flank wear will be more. Then again, coming to feed rate. So feed rate, it is very important parameter. When compared to cutting speed, the feed rate, it will give more influence on the flank wear, right? For rate of feed. So rate of feed, again, what happened? Same thing, increasing feed rate, it is increasing, right? Increasing feed rate, the flank wear is increasing irrespective of all. So even aluminum also, aluminum, blue color is aluminum. Then again, this is TiB2. So when here, flank wear, the 9% composite, more flank wear. 0% composite is, unreinforced alloy is very less flank wear. Whenever increasing feed rate, what happened? The flank wear is increased. Then again, cutting speed versus cutting force. So here, cutting speed versus cutting force. Whenever increasing the cutting speed, cutting force will come down. Okay, cutting force will come down. So irrespective of material, even you take 0%, 0% also it is decreasing. 7.5 also it is decreasing trend. So the reason is, whenever cutting speed is increased, the chip tool contact length, it will be decreased, right? Whenever chip tool contact length is decreases, then the area of contact between the tool and workpiece is decreased. So this less area of contact that reduce the cutting force. So again, what happened? Cutting speed for unreinforced alloy bore. Here, you very interesting to note that. See, composite material are a very lower cutting force. 0% composite, that is unreinforced alloy, it is having more cutting force. The reason is, even lower cutting, even in the irrespective of cutting speed, the build-up edge formation, it will be more. So again, what happened? Build-up edge formation, that will build-up edge deposition over the rack face, that will increase the rack angle. So whenever build-up edge formation is there, the cutting edge is minimized. So whenever cutting edge is minimized, right, then the area of contact will be reduced. So that what happened? Cutting force, it will be maximum. So, and one more thing, the build-up edge also, higher build-up edge also. Again, what happened? It will make more contact. So more area of contact, it will use more friction. So more friction, what happened? Automatically increase the cutting force. That means friction component, it will increase the overall cutting force. So here, cutting force, how we did is Fx, Fy, Fz. So we have taken all the three forces. Resultant force, here we are putting our resultant force. Here we calculated resultant force square root of Fx square plus Fy square, Fz square. So that that value we are putting here. So again, increase in feed rate, cutting force is increased. So increase in feed rate, automatically what happened? The force along the axis of the cutting force. So you are giving feed rate. So more feed rate, cutting force is increased. The more feed rate, the feed force is increased. So of course, feed force is the one of the cutting component, the cutting force component. Increase in feed force, increase the cutting force. Then again, cutting force versus surface roughness. So cutting force increases, surface roughness will come down. So whenever you are machining with very high speed, the build-up edge formation, everything, area of contact is minimized. Already we said. And apart from that, because of high speed, the machine vibration or that little vibration, all the build-up edge, everything, it is flushed out. So that at higher cutting speed, we will get the lower surface roughness. Then again, feed rate versus surface roughness. This is one of the highly influencing parameter, feed rate for surface roughness. If you are increasing feed rate, that what happened? The scratches will come. Even lathe also. You put some practically you can see, right? Fix your mild steel workpiece. Just you rotate the feed rate, feed wheel very higher speed. So that what happened? Tool will vibrate. That vibration, it will cause some feed mass. That feed mass, what happened? That increased the surface roughness. So that 9% composite. So 9% composite, already ceramic content is more. That excess ceramic content also gives some surface roughness. Again, increase in feed rate also, it will increase. Then conclusion. So first something or what happened? These are all characterization based characterization. The machinability of in-situ MMC is different from traditional because of presence of fine and uniformly distributed reinforcement, reduced the flank wear. So that then when machining in-situ composite, higher speed causes rapid tool wear due to generation of high temperature in the machining interface. At higher cutting speed will minimize the chip tool contact length and the build-up edge formation. So build-up edge formation also removed, that reduce the cutting force and the surface roughness. The rate of flank wear, cutting force, surface roughness are high when machining with higher depth of cut. Again, higher depth of cut, because of time constraint, I did not add it. An increase in feed rate increases the flank wear, cutting force and which has surface roughness. So apart from this, even people, you can try for cutting force. Of course, now people are asking the sustainable machining. So you can add one responses, flank wear, cutting force, surface roughness, all are one kind of responses. All are one kind of responses. Even you can add a specific
Sir, excuse me, sir.
Hello? Sir, session is over or not?
हाँ sir, visible.
Madam, session completed or not?
Sir, session is not over. Within 5 minutes, sir, it will be over. Sir, Mahamani, sir, it is in mute, sir, your mic.
Now it is visible, no?
Now, yes, sir.
Yes, yes.
Yes,
Visible, sir.
right, right. Thank you. So this is the fine particle reinforced composite. So in situ, ex situ, I am comparing how it will work. So in situ composite, it is very smaller in size. Even if you are putting into aluminum composite, the depth of the particle is very less. Here you look at that this is a bigger particle, depth is very high when compared to this. Even width also, it is very less. Here width is more. Then if you are going for cutting in situ composite, the particle fracture, here there is no particle pulling. Here the particles are with high interfacial strength. The ceramic particles are getting fractured. So getting fractured, even though if particle pull out is less. So that is here you look at that. So around 75% of reinforcement particle, it is projected away. So this condition when cutting edge meets. Rupa, please mute all the participants. They are making sound.
Yes.
Please mute.
Yes, sir.
Right. So here you look at this. The particles projection is more than 50%. Whenever the cutting edge meeting here, then here you will get the pitch formation. Even though pitch formation also, it is very lower depth. So that the surface roughness, it will not be affected because of this lower. Whereas if you are doing with bigger particle, that is ex situ particles, or reinforcing with bigger particle, then again what happened, if any particle pull out comes, it is going for more depth. This more depth automatically, this will give more surface finish. And again what happened, the voids also formed. So particle is, if you are doing machining ex situ composite, for example SiC or some other particle, so portion of particle is sheared out and remaining particle, it will be stayed like this. Okay. So this will give a crack while going for application, this component going for application. So definitely the mechanical property will be very less. Again, I go for drilling of AA2219, TIB to ZRB2 composite. Here what I am doing is, I am adding TIB2 and ZRB2, K2 TIF6, K2 ZRF6 and KBF4. So here I am giving the composition, right, TIF6. So this is the micro hardness profile. So average for 0% 121, then 3% 143.3, then 6% we got 155 for 6. So here I am using A22219. So this is the copper is the alloying element, the mechanical property of base material itself more. Okay. So these are all the drilling parameters I selected. So here I am selecting drilling speed, feed rate, point angle. Here we are just selecting the high speed steel. We are machining, we are grinding into, initially it will be 120 degree. Your drilling point angle, normally it will be with 120 degree. We grinded and made it into 110. Ruba, mute chema. Right, point angle is 120. Then we grounded 110, 100, 130. Then drill bit diameter we selected 6, 8, 10, 12. These 4. These are all the this diameter widely used, right? So while drilling, spindle speed increases, surface roughness is increased for all the composites, but 6% more composite because 6% reinforcement content is more. So again, feed rate versus surface roughness. Feed rate increases, surface roughness also increases. Okay. So here further 6% composite having more surface roughness. Then again, point angle, if you are increasing point angle, here surface roughness, whenever you are increasing your point angle, so here the surface roughness is increased. So again, 6% composite, we have more, more surface roughness. So here one can ask, sir, 100-degree point angle, you got lower surface roughness. Why you can use? Right, 100-degree, if you are using 100-degree, the material removal rate, it will be lowered, right? So surface roughness is important. At the same time, optimum material removal also important. So that what happened? So 120-degree it is available, optimum material rate. But here in experimental investigation, it shows 100-degree point angle, it gives lower surface roughness. But 100-degree, what happened? It is not suitable. That 100-degree means that will take frequently worn out, and area of contact will reduce. So that what happened? Lower area of contact, material removal rate is lower. Then again, drilling diameter versus surface roughness. As usually, smaller diameter, lower surface roughness, higher diameter more. yeah, even though you look at the variation is very limited. So similarly, spindle speed versus delamination, everything is increased, right? Everything is increased. So here 6% composite in all the observations, the delamination for 6% composite is more. Next, I go to the mechanism. So this is available in my paper. You can see because due to lack of time, I'm just moving. So this is the SEM for the worn out surface. So drill. So cutting edge is there, no worn out cutting edge. So we gone for SEM observation. So you look at this the debrace. So here you look at the worn out. So this is because of higher reinforcement ratio. So we got it made because we are using just HSS cutting tool. Here TiB2 ceramic particle is more harder than HSS. So that you look at that particle scratches are there. And this work I acknowledge. I got MODRAFs while I'm working in Sudarshan Engineering College, 2009. So through MODRAFs we observed, we got the surface roughness and some of the machining response instruments. And also I acknowledge the students, Elvis, Dinesh, these people are done this work. So next I go to studies of grinding studies. So this paper, it is available, I published in 2019, micro manufacturing. Studies on grinding force, size effect, surface structure, everything. So look at that, if you are going for grinding, there are, what happened, these are all the phases are available, various possible interaction. Grinding is somewhat different. Turning is single point cutting tool, drilling is multi-point cutting tool, but grinding, it is different, entirely different. You have many multiple cutting edges are there. Cutting edges are there while doing cutting action, probing, variable interaction, ploughing, then rubbing, right? Rubbing, ploughing, cutting, right? Here cutting, chip bond. So here the various contact may be possible. Chip may contact with bond, chip may contact with workpiece, bond may contact with workpiece. So these are all the various possible interaction in the grinding zone. So here this is my parameter and level. So I selected wheel speed, work speed. I conducted in cylindrical grinding, not surface grinding. Okay. So there wheel rotation speed also available. Grinding depth, feed rate, grinding wheel. Grinding wheel I selected resin bonded diamond wheel and resin bonded CBN wheel. Then vertified AL203. Grinding wheel. I used 3 grinding wheels. So my observation. So here wheel speed on friction force. So we calculated, we estimated friction force, flowing force, and chip formation force. Chip formation force, when you are increasing the wheel speed, what happened here? It is decreasing, right? So you look at this diamond wheel, it is having more friction because diamond means it is a king of all the ceramic material. King of this tool is costly, but this wheel we purchased under Young Scientist grant, diamond wheel. So diamond, it is a material. It will give very good cutting action, and the diamond wheel, it is a very good lubricant. Diamond wheel, it is a very good lubricant, so that it will that lubricating action reduce the friction force considerably. Okay. Then again wheel speed increases, the flowing force comes down. So again, what happened here? So 9 is there, here 3 is there. So 1/3 of ploughing force is reduced if you are using diamond wheel. So influence of wheel speed and chip formation force. Again, chip formation force means how much chip is removed. Here the hardness of the wheel, it will take vital. So among these 3, hardness is more harder. Therefore, when compared to other wheel, the chip formation of the diamond wheel is more. So again, the wheel speed. So wheel speed, specific grinding energy. Specific grinding energy, this is a sustainable machining component. So we added this. So the specific grinding energy, if you are using diamond wheel, it is very less. And CBN wheel is moderate. AL203 wheels, it is more. So similarly, so all the observation we got diamond wheel, it is performing better. So this is the surface roughness. So surface roughness. Again, diamond wheel, it will give more surface roughness. Okay, more chip formation, reducing the friction. So automatically that gives very good surface roughness. So here Al2O3 surface roughness will be poor. Reason is the aluminum chips are there, no, that will be clogging. That means that is entering into the holes in the micro holes in the ceramic wheel surface that will be trapped inside. Once it is trapped, then what happened? The surface roughness, it will be very, very poor. Even increase in work speed, even work speed point of view also, diamond wheel is performing better. Then this is the micro hardness. This is a micro hardness. This is called a subsurface hardness. Subsurface hardness for Al2O3 wheel, 43.98 speed, it is more. So again, this is micro hardness. Al2O3 wheel, 26 meter per minute. This is the work speed. Okay. So here, read again Al2O3, 30 micron grinding size. 30 micron grinding size is giving more subsurface hardness. So this is the what happened? Machined surface analysis. Right here, you look at the diamond wheel generated surface. It is appearing very good. Right. It is appearing very good. Then this is the atomic force microscopic picture. So the optimum cutting conditions we selected. Here you look at that 230 nano we measured. So surface roughness 230 nano it is measured. So again I acknowledging the DST, acknowledging the funding agency DST here. Next, I am going to talk about the reinforcement, the tapping. So drilling, I think, tapping also we did. But this work, we can't make it, we can't bring it at to big level because of various reasons. So here, this is the drilling parameters. This is our component. One cylindrical composite we made and we sliced like that. So again, we used this for tapping. So drilling and tapping, I think, it is a experimental work. It is available in our laboratory, right? One of my MTech Gale students, he did this, right? Here, 0% composite, that tapping, that threaded portion, if you are taking microstructure, it will be like this, okay? Composite material, it will be like this, 3% composite material. Here, tap size is constant, right? The 0% composite, it is appearing like this. The pitch is, the pitch thickness is less. Whereas here the pitch is very high. So here you look at that material is what happened because of reinforcing effect, right? So reinforcement of course increase the hardness, right? It will be like this. So this is a microstructure at 18 magnification. This is 20 magnification. So again, what happened? Same image of thread formed by 6% composite. So it will be like this. So these conclusions you may read from my paper directly. So here, influence of, I'm going to unconventional machining also, we did some studies. So of course, this is not an impact factor journal. So one important thing I want to share is, here I engaged some students. So this Sai Kumar, these people, except one student, remaining all are doing higher studies. One student is doing, completed his MTech Industrial Metallurgy in IIT Kharagpur. Now he is doing PhD. And another, except one remaining all student, they are in Germany. So all are doing their MS in their materials area. So that gives very good initiation. So that's what I am asking. If you are engaging students as part of project work, definitely you can make the students. So all are average student. They made it. So this is the electric discharge machining parameter we selected. So this is the component. Again, we did the L9 component because we are doing BTech level project work. We use L9 layout. So here the current, right? The current increases. So this is about surface roughness. Current increases. Surface roughness is increased. Pulse on time increases. Surface roughness is more. So here you look at that flushing pressure increases. The surface roughness is coming down, but the variation is very less. Okay. Current variation is more, pulse on time is moderate, this is very low. So again, if you are going for analysis of variance, ANOVA, the current it is taking 79.23, around 80% of contribution. on surface roughness. Pulse on time around 12. So remaining flushing pressure. So this mechanism, it is available in papers. So this is the microstructure. So this is the component photographic view of electrochemical EDM machined component. So we look at the surface roughness. This is the microstructure at 100 magnification. We look at the surface. So this is the optimal machining condition. We have taken the surface roughness. Next, I go to laser drilling. This paper, one of my MTech student, Ananda Chakravarti, he did materials and manufacturing process. This is a high impact factor journal. Just MTech project, we published 3 Scopus paper. This is one among that. So this is the laser drilling condition, laser trappening, laser power, standoff distance, right? And so this is the graph. So laser speed, if you are increasing laser speed, entry diameter is decreasing. Increasing laser speed, exit diameter also decreasing. Then laser speed increasing, the taper is increasing. You look at that. So this is one of the finding. Then again, laser power increases. So all the parameters are increased there. I mean, entry diameter, exit diameter. Then again, laser power increases, taper is reducing. So the all the mechanism, everything, it is very clearly described in that paper. Then again, standoff distance increases, entry diameter decreases, then exit diameter also decreases. But the standoff distance, again, here you look at that, standoff distance, the taper is increasing up to 195 standoff distance. So later on it is slowly decreasing. So this is the microstructure available, microstructure for optimal drilling condition, laser trappening speed of 30 mm per second, laser power of 85 watt and standoff distance of 195, picture A. Then picture B, laser trappening speed of 30. So here only difference is 85 and 95. So increasing laser power, what happened? Okay. So this result, so already I discussed. So again, I don't want to read the text. So this is one of my MTech student, he did abrasive finishing machine. This experimental setup we developed in our PT laboratory and we did. So here we are using silicon carbide abrasive we added. Apart from the iron pieces, we added 30 micron silicon carbide powder. Here we selected composite 0, 2.5, 5, 7.5. So here we are using spindle speed of this. And we are using SiC abrasive quantity is 5 grams. The ratio of ferrous and SiC powder is 75-25% we used. Okay. So this is abrasive flow machining. So here speed increases, surface roughness is decreasing for all the conditions. But again, 7.5% of composite. Already I said 7.5% means already the reinforcement content is more. So that what happens, surface roughness, it will be more. Again, speed increases, percentage of change in surface roughness also decreasing. Then finishing rate also decreasing while increasing speed. Then again, if you are adding ferrous particle size, so we are filtering the ferrous particle into different sizes, 100, 150 like that. So there, if you are increasing particle size, surface roughness is increasing. Then percentage of change in surface roughness, again what happened, particle, if you are increasing the particle size, percentage change in surface roughness, it is coming down. So again, finishing rate also, it is in decreasing trend if you are increasing the ferrous particle. This is the speed versus surface roughness. So here you look at that I am making comparison with the addition of SiC, without addition of SiC. If you are adding SiC, then what happened? You will get higher surface roughness, right? Then again, what happened? Percentage of change. If you are increasing percentage of change, again what happened? The dotted line, it is less. Then again, here, if you are increasing speed, the finishing rate is coming down. But look at that, the 5% composite is less than the with SiC. So this is the atomic force microstructure we created. Here you can see that we generated nano surface finish. So nano finish, you can see. Here 939 nano surface we generated. You look at this. So here, if you are using some processing condition, we got a 329 nano surface. So that much lower surface, nano surface finishes we developed. Right. So here my conclusion. K2, mainly I discussed the K2 TiF6, KBF4, K2 sub reaction system. It is widely, nowadays many people are using this. So here the reaction time control is very important. Niranjan and Pierre Lakshmi Narayana, they described the reaction time. If you maintain exactly 20, less or more, what happened? You can't get good mechanical property. And this problem is more than 10%, it is not possible. So we stopped up to 7.5. And the challenges, it is cost effective manufacturing. The composite, aluminum composite, we have recycling issues. Then one more problem for commercial application. For example, you take mild steel, aluminum, this kind of material, you have a design data book. Okay. But the composite material, we don't have a design data for strength, fatigue, creep, wear, corrosion. We don't have a proper design data. So that is one of the major reason for commercial application of this material. But still nowadays, many companies, particularly Chinese people, they initiated. So definitely it will come. India also, shortly it will come. Lack of information about the failure mode. So failure mode, still it is now, it's a big challenge. Then the latest publications, these are all my latest publications. Recently, one of my PhD scholar, he did material innovation, materials engineering and innovation. Then this another paper we published in high temperature tensile behavior of this composite. Then challenges of composite material research. So here I want to explain the challenges. The microstructure study consultancy is very poor. So because of this reason why I am unable to project my research at very high journals, high impact factor journals. So whenever we are sending to some microstructure consultancy, the microstructure clarity is very poor. If I am sending some papers to Science Direct or some other reputed journal, simply they are saying that your microstructure quality is very poor, and simply based on that ground, it will be rejected. Then lack of experimental facility. So, Rupa, you meet the people. Some people are open the mute and talking.
Okay, sir.
Right. So the lack of experimental facility. If you want the lathe tool dynamometer, we are using Chrysler dynamometer. The cost is very high. If you want to purchase, the cost coming around 50 lakhs. Even I have some research funding. I am unable to buy this. And the foundry man is very important. The foundry man, you try in laboratory. Otherwise, what happen? Somewhere you will get a foundry man is there. No, you go to some foundry. You request through your student. Suppose if you are asking that foundry man, he will refuse. If students are requested, some foundry man, they will help the students. My students, they requested on foundry man. Sunday he will do. Remaining day he will work in ferrous metal. Sunday he will make some special furnace and work for the students. Okay. The foundry man, everybody, the students request, they will consider. And the students collaboration is very important. BTech project, MTech project, everything is there. You can engage this work, particularly composite material development, property testing, everything. Students, once if you are engaging and properly motivating, they will do wonders. So this is the one of the important thing I want to share. So here I want to show some of the active researcher in the area of metal machining of composites. So here the Paulo Devim is the one of the bigger, very big scientist. He have 519 Scopus article, right? He is all-rounder. He will do turning, conventional machining and unconventional machining. He will do all the researches. And another person, another professor is Palani Kumar. He is a principal of Sairam Institute of Technology, Chennai. He is having 220. So mainly he will do fiber composite, fiber reinforced composite, and used to have more drilling, and some conventional machining also he did. And one more scientist at Coimbatore PhD College of Technology, Krishnaraj, he will frequently he will conduct some short seminar or workshop. So I am the frequent follower of this. And another scientist is IIT Madras, Dr. L. Vijayaraghavan. He is also involving research in machinability of composite. Particularly, he did more work in grinding. My grindability issues project, grindability study of composite machining project, I followed him. Here we need to understand somebody they crossed it, disturbed my sharing. Right. So, Vijay Raghavan sir, so here we need to appreciate who are all the scientists. So here, why I am presenting this, I am not calling myself as a big research in the area. So I need to inform the some people. They are like my senior follower. Since 2009, past 10 years, I am following these people. If you want to do any research on composite material and machining, if you are following the scientists, definitely you will get it. You will get more information, more knowledge. And unconventional machining, there are two people. Great. One is V.K. Jain. He is author of unconventional. They both are from IIT Kanpur. He is having 157 documents. Particularly, he will do research in unconventional machining. And again, Ram Kumar Janagarajan, he belongs to Trichy. He is working in IIT Kanpur. He is one of the biggest scientists in the area of composite machining and other material also he machine. He is good. He is doing machining at unconventional machining. Now I think again coming back to, so I think you have attended this webinar. So past 1.5 hours I struggled you. So you can able to get some knowledge, synthesis, aluminum based composite, microstructure study. You can do it at laboratory, right? And you can go for some conference. Nowadays, if you are attending conference, you will get the Scopus indexing conference. You can apply. Conducting machining studies, just purchase one dynamometer for 40,000 and you can do your research in the lab itself. Even drilling, you can do that like me, like delamination, measuring the surface roughness and the burr height. This kind of work you can do it at your laboratory itself. And collaborate with students and conduct. So this is the one of the good way to do. So students, they will gain knowledge and you will also gain some knowledge through the students' work. And you can go for some collaborated published work. So the students will appreciate it. Students will get higher education, everything. This publication, it is really helping them. Then mechanism of material removal is very important. So all the paper, some conference paper, if you look at that, simply they will put the observation. They will not explain the mechanism. Explaining mechanism is in detail is very important. Then before thank that, yeah. So stay home and stay safe. Thank you one and all. And before concluding that, yeah, big salute to COVID-19 or coronavirus fighter. So if you have any queries, you put it into the chat box. I hope Rupa, you please help me to show the questions on the screen.
Sir.
If possible, I will clarify now. If not possible, you send to email ID. First page, my email ID is there. You send to your questions.
Okay, sir.
I will reply.
Okay. Okay,
Rupa, you post the question. You go to chat box. If you have any questions, you show on the screen.
Sir. 1 minute, sir. I will present my screen, sir. Then.
Okay, fine.
Sir.
Yeah.
No, sir. No questions, sir. Actually, they're asking to present a PPT, sir.
Okay, you are sending video recording to all the people.
Okay, sir.
So that it is okay.
Okay, sir.
So any other questions? If you have any questions, please. Yeah, there is a question came. Muthu CT. Yeah, you open that, please.
Is it possible to study molecular level simulation for composites?
Normally, this is for CT, somebody, yeah. So here, so far I didn't conducted film analysis, film study, but it is possible. Some laser-based machining, it is possible. Some people from NIT Trichy, they are doing this research, machining simulation. So initially, I tried the machining simulation at composite material developing and machining. It is not that much easy. The simulation, everything without experimental validation, people will not accept. Simply, I won't go for simulation. So generally, I will go for experimental based work. right? But I request you to some laser-based machining and electron beam machining. This kind of machining, the machining, it will take more cost. So facility is very limited. That kind of costly machining like laser machining, electron beam machining, you can go for simulation. So you can go for 1/3 of experimental layout. You can go with experimental work. Remaining thing you can go for simulation. Right. Next month.
Sir, good afternoon, sir.
Good afternoon, sir.
Myself Ajay Kumar.
Yeah, please, sir.
Sir, generally in most of the research in the composite materials, is there any scientific way to select the percentages of fiber and matrix material? Because I have referred many number of papers. Simply they will
Yes, sir.
give 70,
Yes, sir.
30, 80, 20 like that.
Yes, sir. Here, the one important thing is the composite materials are tailor-made. Based on your requirement, you can develop. Based on your requirement, you can develop. Suppose if you want more strength, you can increase the fiber content. Right? So this is the way they are following. It's a tailorability. You can vary. Here, what to do is you can. There is no standard. Right? There is no standard, and if you are going more than 40%, automatically the material strength it will be increased, but the workability is very important. So reason for discussing the machinability issues, machinability related issue is the component it should go for application. So my composite property is very good. I cannot keep it into the exhibition. So it need to go for application. More fiber content, it will be restricted the applications. So normally people go for up to 40, they will go. More than 40, what happened means which limits the application. Simply developing mechanical property, everything, it is good. It is one way of research. But real-time application, the fiber content, low fiber content is required. Okay.
Okay. Thank you, sir.
Right.
Sir, other questions, can I mail you, sir? Can we
Right. I will
answer?
take one more question I
Okay,
answered.
sir.
Then remaining thing you send to my email. I will send
Okay,
it.
sir.
Mm,
Okay,
right.
sir.
Only one question you read. Somebody they asked now. Yes.
Sir, can you suggest recent work composite materials used in the automobile?
So also automobile people they are going. So that's what I said. Even nowadays the nano composites, reinforcing nano size particles, particularly carbon nanotube. This kind of composite it is widely used. So nano composite material, there is a workshop. It is happening one college. Nano composite synthesis, right? Nano composite synthesis is the reinforcement is costly, but at the same time, if you are reinforcing 2 to 3%, we will get very good properties. So, and we will get all the required mechanical property. So, only problem is the reinforcement cost is very high. So, nowadays people they are going for nano composites also, carbon nanotubes. Some people they are going for particle fiber mixed, right? Particle fiber mixed. So, developing nano composite and conducting machinability, formability, and other study. So, you don't leave it simply studying mechanical property and wear property. So, we are a mechanical engineer. Of course, bringing the component into the real-time application is very important. Okay. So, you can go for nano-based synthesizing nano-based composite and conducting various property studies. Right, remaining question you sent to email ID. So email my first slide. It is available. My email
Okay,
ID
sir,
is available. You send
Okay,
the
sir.
questions directly to me. I will reply. Okay.
Okay, sir. Thank
Right,
you, sir.
it is over from my end, please.
Okay, sir.
Yeah.
On behalf of the Mechanical Engineering Department, I extend a very heartily vote of thanks to the Honorable Speaker who blessed us with their presence and took out valuable time of your busy schedule, sir. I must mention our deep sense of appreciation for Dr. Mahamani, sir, for his work. Also, I would like to extend a special thanks to Dr. Rajshekar Patil, sir, for inspiring us and for providing the encouragement and his support. And I extend my big thanks to the participants and our department faculty for their support. Thank you all for making this event successful with your contribution. Sir Patil, sir, over to you, sir. Thank you, sir. HOD, sir.
Yeah.
Sir, it's
Madam, one
ah,
second.
sir. Over to you.
Professor, I thank you
Okay,
very
sir.
much. I found it really insightful and also, sir, once again, mechanical engineering. Is it audible, madam?
No, sir.
Yes.
Hello.
Yeah, Professor, thank you very much.
Thank you, sir.
I found it really insightful and interesting, sir. And also, you have given lot of input to our BTech level, master, and also doctoral level. And you have given a lot of inputs. I think all the participants, they have to use these particular inputs and do something better for our society. So, from School of Engineering and Technology, CMR University, Department of Mechanical Engineering. So, our wholehearted thanks to you, sir, for accepting our invitation and delivering this online lecture for all of us. Thank you very much.
Thank you, sir. Thank you.
The letter of appreciation from our side. I request
Yes.
Madam, she is presenting.
Yes.
This is what
Yes, sir.
please accept our digital letter of appreciation, sir. Thank you very
Yes,
much.
sir. Yes, sir. Thank you.
Thank you.
Rupa, can I leave now?
Yes, madam. Any final words? Please tell and if
Nothing, sir. Feedback form and presentation and these questions I will send to participants' mail, sir.
Okay, sir. Okay, okay.
Sir, okay, sir.
This recording also you
Thank
can
you,
send.
sir.
Video recording also you can send to. You upload in YouTube. That YouTube link you can share to participant, so that
Okay.
yeah.
they will get. They will keep
Actually,
for all
we
time.
have a procedure.
Yes, sir.
Okay, sir. Okay, sir. I will
Sir, we
upload.
have a procedure. We'll make beautiful report.
Yes,
And that
sir.
complete report with feedback we will send you, sir.
Fine, sir. Very good, sir. Yes. Thank you.
Thank you.
Okay, sir. Thank you, sir.
Right.